In this video, we are going to go over two different pseudocodes for the Dijkstras shortest path algorithm. The first pseudocode maps to the worked example we just did, and it's from the Mark Weiss book. The second pseudocode is another one from Corman's book, and it's more predominantly used for implementation purposes. So I thought I should include that in these slides. So the first one, like here, it describes that we need again like four different data structures, two sets and two arrays. We initialize S with the start vertex, which is S. So initialize S initially contains just our start vertex. For the previous example, it was just 0. And V minus S contains all the vertices except the start vertex or the source vertex. So it will have 1, 2, 3, and 4. Next, like all these lines from 2 to 6 is basically the initialization step. We still haven't finished processing the algorithm. So in this step, what we are going to do is for every vertex that is in V minus S, which is all these vertices, we are going to set the previous vertex, like PV is the predecessor vertex, to S. So initially we decided to keep it -1, but you can also keep it to the source and it will work the same way. Next, if there's an edge from S to V for each vertex, like if there's an edge from 0 to 1, from 0 to 2, 0 to 3, or 0 to 4, you initialize dv to that weight of the vertex. So essentially what they are trying to do is, in the first step, all of these were, I'm so sorry, initially we had this source equal to 0 and all of these were infinities. In their initialization of in the pseudocode, what they are just doing is, instead of initializing everything to infinity, they are initializing all the first connected vertices to the source vertex to the value of the edges. So it's going to be 10 and 60, but the other ones are still going to be infinite. So you can initialize it either way. The problem will still work in both ways. Next, they run the algorithm till v minus s is empty. So they remove each vertex from the set v minus s that has the smallest du. So you remember, like we were trying to find which is the smallest dv or du in this table that we have, which is the smallest value, and you're going to remove this vertex from the here to the computed set. So that's what they are exactly doing. So for every v that they have found that is adjacent to u, so again what they are trying to do is, what are the adjacent values that are here. So now they are performing the relaxation. They remove, uh, so they calculate du plus the weight of the edge from u to v. If that is less than dv, then you set the dv to du plus the weight of the vertex. So essentially what we were doing, they are exactly doing the same, and you set the predecessor to the u vertex if the relaxation is successful. This equation is exactly same as I showed you in one of the slides earlier, which is when I was describing what is a relaxation. Right here, the equation in the pseudocode is exactly the same, so you do not have to worry. There's also a proof regarding this, but since this is not the grad level course, if you go to a grad level course or if you just search online for the proof of Dijkstras algorithm, uh, it's a pretty intuitive proof, on why relaxation will always work. We are not going to cover this in this course, but if you are curious to know, just like search online and you'll find it. And if anybody needs help, just get back to me. Now, the complexity of this algorithm is less doable, like when it's more computationally expensive if we implement it as in this way. So that's why I'm going to show you another pseudocode which describes, which uh, reduces the complexity of the code by choosing a data structure which is priority queue. And priority queue is basically heaps, which we have already covered. And why that data structure is helpful here is that you remember, like every time we were taking these dv's, because we are trying to find out what is the minimum dv in this operation. So that is going to be computationally more expensive. But if we maintain a priority queue, we can find the minimum value, because essentially the priority queue is a min heap, right? In O1 complexity, and we can remove the minimum element from this priority queue in log n complexity, because essentially what we are trying to do is, initially we have all these values as 0 and infinities. So we perform the relaxation, and when what we are basically doing is, when we are performing relaxation, we are changing this infinity or a greater value to a lesser value. So in case of heaps, we are performing the operation called decrease key. Okay, you can also do a remove operation, and then you can add it, and it's still going to be same because those are going to be two independent operation. But essentially the decrease key one is more popular. Like whenever you implement a heap interface or a priority queue interface, this decrease key takes in a vertex, and it decreases the priority, which is in this case, these DVs are priorities. So initially 0 will have the highest priority because it's a min heap that we'll be implementing in the second pseudocode we are going to see. And infinites will have lower priority because they will be lower in that heap. When we perform a decrease key operation, we are going to change this infinity to a lower value, and we are going to heapify up, because we know all the values below this are going to be greater, because it's a priority queue and all the values below it are already greater. So if we change this value from infinite to 10, we just have to worry about what's above this, and this will take like log n times, because the uh, we just need to perform the operation heapify up, which we saw right before, right when we covered heaps. So this is this other pseudocode that I was talking about that requires priority queue. So how this works is, I do not have the time to visualize this, but if you do it on a piece of paper, you'll see that you'll find the exact same results, and it's pretty straightforward. So you can perform either ways. Like if you want to do the tabular way to calculate these numbers, that's fine. If you prefer this way, that's absolutely fine too. So initially you'll have a priority queue. This priority queue, you'll add the source vertex with the value 0. So in our case, like we had 0, 1, 2, 3, 4, like these were the four things in our graph. So you initialize a priority queue or a heap data structure, which will have on top 0, because 0 was passed as a source with priority 0. All the other vertices in this would look something like this. 1 will have the priority infinity, 2 will have the priority infinity, 3 will have infinite, and 4 will have infinite. Okay, probably our structure will look like this. So 0, 1, 2, 3, 4 are just labels. Uh, and the actual priority, or the core thing behind our priority queue, are these numbers, which are the dv values. So we add into the priority queue all the other vertices, the value infinite, as I just showed you. Now you repeat this process till the priority queue is not empty. You find the vertex with the lowest priority, so in this case it will be 0. You remove that from the priority queue, and once you do removal of this, it will again like take log n complexity, because to remove an element from a priority queue, you replace it with the last element and kind of heapify down, which we have already covered. Next, you relax all edges that are adjacent to p. So we already have a function called get adjacent or something. You perform the relaxation part at every edge. So this relaxation could be right here, or you can have that as a standalone function. You are basically checking if du plus weight, like the for every edge u to v, you're going to check if the distance the shortest distance to u plus the weight of the vertex is less than the shortest current distance at v, then we are going to replace the current distance of v with du plus weight. And we are going to change the previous vertex to u because now the predecessor would be u in this case. Next, we are also going to change the priority of v, the vertex v. Like let's say if we were doing for 0 was connected to 1 with value 10. So now instead of 1 with infinity, you are going to change 1's value with the value 10 and so on. And this is going to work till our priority queue is not empty. And you are going to repeat this process. So let's see what would be the complexity for this code. Here, when you add one particular value to a priority queue, the complexity is log of n, or in this case, since we are adding v vertices, because we are again and again adding v different vertices, it's going to be v log v. Next, for this particular code, we are basically having in the priority queue v elements. For each element, we are going to compute this remove smallest operation, which it again takes like log v complexity. So that's why like this part will also be have time complexity of o of v log v. The next part is we are going to relax all edges from this vertex. So this edge operation, it's going to compute the edges, like it's going to relax the edges for each edge exactly once in the graph. There's supposed to be proof behind it. So for that particular case, like for each directed edge, it's going to just relax once. So we are repeating all these lines of code e times, where e is the number of edges. And we are also performing this change priority operation at every relaxation, every successful relaxation. So although this relaxation will only work for some edges it will fail, this step will take log of v time to change the priority, because in the priority queue there are v elements. So the total complexity for this code is going to be O of V log V plus V log V plus E log V. So again, you do not need to remember all the complexities or the pseudocodes. We know like this is difficult unless we ask you to bring cheat sheets or something. We won't be asking you like these complexities or like to write the pseudocode for this algorithm. What you should conceptually know is how the numbers are manipulated and how would the shortest path look like if we give you a graph for any source vertex to any other vertex. Like we will provide you a source and you need to compute the Dijkstras algorithm. Just to sum up, the algorithm that we just discussed is a form of greedy algorithm. We are going to cover greedy algorithms. There's an entire week to it after a couple of weeks. So I'm not going to discuss, but it gives you like it's a greedy algorithm because it visits the vertices in the order of best known distance from the source. Another thing is it's guaranteed to return a correct result, and it is also guaranteed to return you an optimal result. So there are some algorithms which might give you the correct result, but that might not be the best result. But Dijkstra is guaranteed both of them. Again, we do not cover the proofs for these because it's outside the scope of class and it's too mathematically extensive to cover it in like a lecture. Finally, the runtime is O V log V plus V log V and E log V. Since E is much greater than V, or E will always be greater than V, we can reduce this to E O of E log V for a connected graph. That's pretty much it. So if you have any questions, visit me in the office hours. Thank you.